Center for the Ethiopian Educational Information and Communication Technology presents Educational Satellite Television Programs.
Hello teacher, hello students. Welcome to a new unit on the applications of differential calculus. In this unit, we will learn to find the local minimum and maximum values of a function, as well its absolute maximum and minimum values. We will learn about the mean value theorem and solve problems in which the theorems, formulae, and procedures of differential calculus are applied. We are going to begin by defining critical numbers and the maximum and minimum values of a function on a closed interval. Are you ready, students? The fundamental theorem of algebra states that every nth degree polynomial has, at most, n real zeros. The problem of finding zeros of a polynomial is the same as the problem of factorizing the polynomial into linear or quadratic factors. In previous grades, we have studied how to find the zeros of a function. Note that a number c is a zero of a function f if and only if f of c is 0. Now, let us learn about the values of a function on a set. Let f be a function defined on set S. If, for some c in S, f of c is greater than or equal to f of x for every x in S, then f of c is called an absolute maximum of f on S. If f of c is less than or equal to f of x for every x in S, then f of c is called an absolute minimum of f on S. The absolute maximum and absolute minimum of f on S are called extreme values, or the absolute extreme values of f on S. If the context is clear, we can simply use the terms maximum and minimum instead of absolute maximum or absolute minimum. If a function f is continuous on a closed, bounded interval, then both the absolute maximum and absolute minimum must occur. This is called the extreme value theorem. Let a function f be continuous on a closed, bounded interval a, b. Then f has both the absolute maximum and absolute minimum values on the interval. From this graph, we can see that f of a is less than or equal to f of x, which is less than or equal to f of c for all x in the closed interval ab. Therefore, we can conclude that f of a is the absolute minimum and f of c is the absolute maximum value of f of the closed interval ab. Be sure to note that this theorem does not tell us where and how to find the maximum and minimum values in the interval. It simply demonstrates that a continuous function on a closed and bounded interval has extreme values. Sometimes there are extreme values even when these conditions are not satisfied. But if the conditions apply, the existence of extreme values is guaranteed. It is time for our first activity, everyone. Observe this graph. Please try to identify the numbers at which the maximum or minimum values occur on the given interval.
Students, let's get ready. Begin. Time's up! Let's get back to our lesson.
Welcome back, students. Have you finished with the activity? Good. Then let us examine your answers together. On the first interval, the maximum occurs at A, and the minimum occurs at C1. On the second interval, the maximum occurs at C2, and the minimum occurs at C3. On the third interval, the maximum occurs at C4, and the minimum occurs at C3. On the fourth interval, the maximum occurs at C4, and the minimum occurs at B. Good work, everyone. Notice the horizontal tangent lines? Their presence means that the slope of the tangent line is 0. Therefore, the derivatives of C1, C3, and C4 are equal to 0. No tangent line can be drawn at C2, f of C2. Therefore, we can say that the derivative of f does not exist at C2. These observations lead us to a theorem. If a continuous function f has a relative extremum at C, then either f prime of C equals 0 or f has no derivative of C. The converse holds true as well. Let C be in the domain of f. Then if f prime of C equals 0 or f has no derivative at C, then C is said to be a critical number of f. It is time for our second activity. Working with a partner, find the critical number of this function.
Students, let's get ready. Begin. Time's up. Let's get back to our lesson.
Hello again. First, let us find the derivative of the function. Now that we have found f prime, we know that it is defined for all values of x. Let us solve the derivative like a normal quadrilateral. We must factorize it in order to find the roots. In this case, either 5x plus 1 or 3x plus 3 must equal 0. In other words, 5x must equal -1 or 3x must equal -3. Therefore, the critical numbers of the function are -1 over 5 and -1. Did you find the same answer, students? If so, very well done. Today, we have learned about maximum and minimum values and critical points. Until next lesson, thank you, teacher. Thank you, students.